Modern human infrastructure is a brute force exercise. We build dense concrete environments, and then we burn significant amounts of external energy to pump heat away and fight the local climate. Many natural systems solve these same physical problems with minimal wasted effort. Look at molluscan biomineralization. As the nautilus grows, it secretes a shell that expands outward in a precise equiangular trajectory, a logarithmic spiral. Scale up 1,000,000 meters. Atmospheric hydrodynamics and Coriolis vorticity organize massive storm systems over the ocean, spinning tropical cyclones into the same shape. Scale up 21 orders of magnitude. Gravitational density waves compress interstellar gas across galactic disks, triggering star formation along these identical sweeping curves. If we extract the geometry of these three systems and stack them together, we see a match. Despite operating under different physical forces, biomineralization, hydrodynamics, and gravity, they all converge on the same trajectory. This convergence reveals a scale-invariant geometric archetype, a structural logic that remains consistent from a single shell to the spiral arms of a galaxy. Biological organisms face strict metabolic constraints. For a honeybee, synthesizing wax requires consuming roughly 8 grams of digested honey for every single gram of wax produced. This creates a pressure to maximize storage volume while minimizing material output. This is the honeycomb conjecture. To partition a flat surface into cells of equal area without leaving empty gaps, only 3 regular polygons can form a continuous tiling: the equilateral triangle, the square, and the regular hexagon. As the perimeter calculations show, the regular hexagon minimizes the total boundary required to enclose a given unit area. It provides maximum storage space for minimum amount of wax. The bees achieve this through a viscoelastic transition. They secrete circular cylinders first, then use metabolic body heat to warm the hive. Surface tension naturally pulls the softening wax flat, snapping the walls into 120-degree angles. The final result is a structurally stable lattice built with mathematical precision. In a world of finite resources, isoperimetric geometry provides the solution. The math creates the efficiency that additional material cannot. Distribution presents another physical constraint: how an organism can fit immense structural complexity and surface area into a limited 3-dimensional space. In 1975, Benoit Mandelbrot formulated a way to measure this. He coined the term fractal geometry to describe natural shapes that traditional Euclidean geometry cannot adequately model. This model demonstrates the Hauster-Basikovich dimension, the core metric of fractal complexity. The shape retains self-similarity across all spatial scales. No matter the magnification, the structure repeats the same efficient pattern rather than smoothing out. Sunflower seeds arrange themselves using interlocking Fermat spirals, governed by the golden angle. This fractal layout produces the highest possible packing density, fitting the maximum number of seeds onto a circular receptacle without overlap. The human cardiovascular system utilizes this same geometry. It branches 10 billion microvessels to deliver oxygen within micrometers of nearly every cell in the body, while using less than 2 watts of metabolic power. Fractal self-similarity is a universal algorithm for maximizing functional contact area while minimizing energy consumption. The city of Harare, Zimbabwe, experiences aggressive daily temperature swings. The environment cycles between sub-freezing nights and daytime heat reaching 40 degrees Celsius. Most commercial architecture handles this by sealing the interior and relying on power-hungry mechanical HVAC equipment to maintain a stable climate. Indigenous macrotermites in the same region use a biological alternative. Their earthen mounds maintain a stable internal microclimate passively. This cross-section shows the mound acting as a fluidic pump. Metabolic heat generated by the colony drives warm air upward, forcing it out through central chimneys. This upward draft pulls cooler, fresh air inward through low-level conduits, stabilizing the core around 30 degrees Celsius. These biological structures utilize local geometry and natural convection currents to successfully manage environmental stress without the need for external electricity. Architect Mick Pierce translated this termite thermoregulation into a 5,600 square meter commercial complex, Harare's Eastgate Center. During the daytime, the heavy, exposed concrete floor slabs act as a high-capacity thermal mass. The concrete absorbs internal heat generated by occupants and equipment, slowing the building's temperature rise. Here is the nighttime flushing cycle. Low-energy fans draw cool outdoor air through hollow channels cast directly inside the concrete slabs. This air absorbs the trapped daytime's heat and vents it vertically out through 9 rooftop chimneys. A passive solar strategy restricts window glass to just 25% of the facade. Deep recesses and concrete overhangs block the high summer sun, reducing solar heat gain. The operational data confirms the efficiency of this design. The Eastgate Center uses 90% less HVAC energy than a conventional tower of the same size, saving $3.5 million in upfront capital costs. Modern engineering can reduce its energy footprint by adopting these geometric principles. This is the Japanese Shinkansen bullet train. In its early iterations, its blunt front mows created a severe environmental bottleneck during operation. The issue was the physics of a tunnel boom. When a blunt object displaces air rapidly inside a confined tunnel, it compresses the atmosphere in front of it. Upon exiting the tunnel, that pressurized air explodes outward as a microsonic shockwave. This pressure wave violated noise regulations and caused repeated structural fatigue to the concrete tunnels. To solve it, engineers applied biomimicry. They bypassed expensive trial and error by copying structural principles that evolution had already refined through millions of years of optimization. Nature's solution for transitioning between differing fluid resistances is the kingfisher bird. It dives from low-resistance air into high-resistance water without creating a splash. The mechanism lies in the specific morphology of its beak. It features an optimized wedge geometry that cleanly slices through pressure waves, rather than compressing the fluid ahead of it. Here, the kingfisher's beak maps directly onto a redesigned front nose for the Shinkansen train. The simulated airflow lines now slice cleanly over the wedge. As they smooth out and air shear resistance drops, the data confirms the geometric adjustment eliminated the microsonic shockwave. This form also provided secondary engineering benefits, significantly reducing air drag and generating a major increase in the train's overall energy efficiency. The geometric patterns found in nature provide a functional language for achieving peak physical optimization and structural durability.